momentarily see recording start, and then Dan, I believe you're going to kick us off.
Yeah, and I'll keep my intro really short. So this is the description of some of the work that's on the IPDK website, and so I'll let Artsiom and Filip start it off. Thank you.
Thank you, Dan. Thank you, Kate. So in this presentation, our focus will be on the current state of development of storage solutions in IPDK. And as the title says, we are going to focus on virtualized and disaggregated block storage in IPDK using a containerized simulation environment. So the structure of the presentation is pretty simple. So we will start with putting our solution in some bigger context. So showing what problems are we actually solving. Then we will switch to the main part, which is a live demo of our solution. And we will finish with enumerating of our next steps that we are working on. So from a user application point of view, we do not really care what particular hardware we are accessing. So one problem that we would like to solve is to provide abstraction over hardware storage resources. Also, the storage does not need to be locally attached. So we would like to have a possibility of disaggregate the storage, to have a remote access to it. And also, whatever application the client is running, this must not be modified just because of using this, let's say, modified way of accessing storage. So the same standard type of drivers should be in use, and the application should be fully transparent of what's behind. And this graphics kind of illustrates this. So we have some host complex. There is some operating system or a hypervisor. There are some standard drivers in use, and storage is being accessed. So to the application, it looks like a physically attached local storage. But what happens in the background, we have another device, which we call at Intel IPU, so infrastructure processing unit, which basically offloads this storage service from host and enables over network remote access to some real storage target. And today, our focus will be on host-facing virtio-blk interface and the connection to a remote storage target will happen over NVMe-oTCP protocol. So this is basically the summary of the problem statement and the solution. But IPDK together with an IPU gives some additional benefits to this solution. So with an IPU, we most of all want to gain on performance. And if we have a real hardware device which takes care of the storage related computations, which basically frees up the CPU cores of the client and also takes advantage of modern technologies, then we can have a big performance boost because of the usage of such an accelerator. Also, what we do want is to have a hot-plug possibility of storage devices. So this is indicated in these graphics with a different number of lines going into the cloud from the different systems. So we basically dynamically want to say, give me another storage device here, give me another storage device there. And also the solution is supposed to be fully hardware and vendor agnostic. In the graphics, this is indicated for different vendors here with different colors, and for different IPUs here with these different device descriptions. Also, if we are supposed to, if our solution is supposed to work on different hardwares, we need some kind of an easy way to deploy this solution. And we have decided to go for containers. So as long as a component of this system, so here you have some detailed view of the host complex and IPU, and here is a detailed view of this remote storage target. So yellow boxes are containers. And the containers have the advantage that as long as the particular system supports some container runtime, we can just easily deploy containers on that system. And containers are basically clearly defined reference system. So you have some kind of a recipe, you download it, you build the container, you deploy the container, and all the same flows should work for hardware A and for hardware B. And another thing is that if you want to try this solution, maybe you don't want to buy the hardware just to try it out. So what we also strive to achieve with our solution is the enablement of rapid prototyping of a software-based IPU target. So we basically provide an IPU container, which is purely software-based, and you can basically play with the solution, try to adjust it to your own use cases, and see if it works for you. And then you can decide, okay, I'm happy with this solution, but now I want it to be really fast. So I would like to buy some hardware. So you buy the hardware, you plug it in, you put a container-specific hardware on the IPU, or you just install the software stack directly on the IPU, and the same flows you exercise with your software-based target should work exactly the same way. Here we have some detailed view of the diagrams I kind of briefly showed on the previous slide. And for the detailed view, I would like Artsiom to take the stage. So Artsiom, please.
Thank you, Filip.
Just to check, is this the correct slide? Oh, you just shared. Excellent. Thank you.
Yeah, so I need to take control. Just a second. Yeah. So first of all, I'd like to start with our hardware case, right? And let's have a look into the legend here. So we've got interfaces in green, and we've got containers in yellow, and we've got exposed devices in blue, right? As you can see, we've got three containers here. The first one is host target, which is able to exercise different virtio-blk devices, right? By sending FIO traffic over there. And this container exposes very simple gRPC interface, right? Those virtio-blk devices, they're exposed by another container, which is called here IPU storage container, right? And that container is able to connect to remote NVMe storage and expose the namespaces as virtio-blk devices to host, right? And also the overall control is performed by SPDK SMA interface, which is which can be easily extended to any other IPU by providing a separate plugin. And the next container is storage target. That one is responsible for providing ideal storage device like RAM drive, and it exposes it over NVMe, and the interface in that case is standard SPDK JSON RPC, right?
Can we ask questions now, or do you want us to hold?
Please do. So yeah,
you can ask. Okay, I don't want to interrupt your flow. That's why I'm just checking, right? So there are two things that you seem to be doing, right? One is the storage and storage interface APIs, right? You also seem to be doing how will that storage get consumed. So you are putting some effort on the containers and the stack through which you access that storage, right? I'm not a storage guy, so I'm trying to understand. So you're trying to do both. IPU DPU creates an interface to external storage, and also you're looking at the stack that allows you to consume. You seem to be doing some container work so that people can access whatever you have or consume it easily.
Well, probably you'll see later, right? And during the demonstration, right?
Oh, okay.
Yeah.
So don't forget we have a live demo. So I think that we will just basically go through the presentation first, and then we will leave space for Q&A, and we can go back to whatever slide we like.
I got it. Thank you.
Yeah, and just a note that we are actively working on that hardware case. If you're interested in that, so please contact Intel, right? Yeah, and if you talk about software solution, right? So it is very similar to the hardware case, but we've got a single, physical platform which feeds simulated host and simulated IPU here. And simulated IPU is represented by a running QEMU instance, and simulated host is represented by running QEMU instance, and simulated IPU is represented by running dedicated container, which is able to communicate with that QEMU instance, right? And this this solution will be shown in today's demo, right? And what I'm going to demonstrate is just, let's try to create 64 virtio-blk disks, right? Run traffic over a disk, right? And then we try to hot unplug them. And now it's demo time.
Artsiom, because we have these slides here, and let me know if we should proceed the slides, so that we don't get out of sync. So now we are on the right slide.
Yes.
So these
after
are
the presentation, we can switch to the next, right?
Sure. So now it's the time for the first demo. So this is going to be an interactive one, and here you can see the scenarios that are going to be covered in this demo. So hot plugging and unplugging multiple virtio disks, and running some exemplary FIO traffic to one of the attached disks.
Yeah. So I'll share my screen. Yeah. Just a second. Just let me know if you can see it.
Yeah.
Okay, so here we have a bunch of tabs, and all of them, they are connected to the appropriate components on the diagram, right? And currently we are on the QEMU tab, so let's check that we don't have, don't have any virtio-blk devices attached, and we've got our host target container running. That's fine. On this tab, we've got our APU storage container running. You can see that SPDK is up and running, and storage target the same, right? And user tab, it will be used just to send different commands, right? So first of all, let's try to create a subsystem on storage target. So it is just a shell function, but inside we send just a simple request. So we have created a subsystem on storage target by this way. The next step, let's create 64 RAM drives on storage target. So we are going the same basically way. We create RAM drives, we attach them to the subsystem, right? And that subsystem is exposed as an NVMe device to the outer world, right? Yeah, we are done, I suppose. And the next step, let's create our virtio-blk devices, right? So currently we are going this way through SPDK SMA. Internally, we've got a provided plugin, which is able to connect to remote NVMe target. And inside that plugin, we expose the namespaces as vhost virtio-blks, and we attach those virtio-blks devices over QEMU monitor to the running QEMU instance, right? This SPDK SMA, as I mentioned, it can be easily extended to any other platform. So if you want to adapt, you just need to provide a plugin for your IPU, and basically that's all, right? And it is a bit lengthy operation. We can switch to other tab. For example, on VM, we can see some kernel logs notifying about devices. On APU storage, we can see some SPDK logs. And I suppose we are done here. Let's switch to VM and let's check virtio-blk devices. So here we can see many of them. Let's try to calculate their number. So we've got 64 of them, right? As a next step, we can send some traffic, right? So let's try to send traffic to the very first virtio-blk device created. So let's see. Here you can see FIO output, and here you can observe that the traffic was sent over VDA device, right? Also, you can try to accessorize any other devices, for example, 10th in this array. So let's run traffic, and here you can see that VDK was exercised this time, right? Next, let's try to delete hot-unplug all those devices, right? With hot-unplugging, we go to APU storage container, right? And inside SPDK SMA plugin, we just go to QEMU instance monitor, and we are unplugging those devices, right? Let's get back to our VM, and let's check that we don't have any block devices, right? virtio-blk devices. As you can see here, we don't have any, right? So yeah, suppose that this part of demo is over, so we can get back to the presentation.
Kate, can you share the presentation slides again?
Yeah, probably.
I'm
This one.
going.
Yeah.
Exactly. So we are after the demo, and now let's talk about the tests which are integrated with our solution.
Yes. So we've got a bunch of integration tests for KVM target only right now. Those tests, they're based on Docker Compose. Docker Compose is used just to run and build and run all the containers and provide the environment for their execution, like create network, assign IP addresses, so on, so on. And additionally, we've got some containers like traffic generator, and we've got QEMU instance inside that container. And also we've got test driver, which is able to execute different test scenarios, like, like the one I've just demonstrated. Internally, it's just sends different commands like create subsystem, create run drive, attach virtio-blk, send FIO traffic, and so on and so on. Currently we've got 3 test cases. In the first one, we attach virtio-blk, detach and reattach it again, and check all the time that we've got the required number of virtio-blk devices, right? In the second, we run FIO traffic over one of the devices. And in the third one, we demonstrate our scale-out scenario. We attach 64 virtio-blk disks, and then we detach them, right? And suppose it's demo time again. Just a second. Yeah. So our diagram. Let's switch to the test. Let's try to run only one test just to save up our time. Also, I'd like to mention that we've been trying to make the test as easily runnable as possible. So you just need to install some dependencies, right? And just hit run sh. And as you can see, the test script, it will try to build all the containers, right? Prepare the environment. And when it's ready, it will start all the containers. Yeah. And here you can observe that Docker Compose, it is getting together all the logs from the different containers. So you can observe here, for example, IPU storage container log and test driver log. As you can see here, we've got QEMU instance. So we just need to wait a bit when that OS inside that QEMU is up and running, just to proceed. And for example, here you can see that test driver was able to get some boot logs from QEMU instance, right? So when the boot is ready, after that, we'll attach one virtio-blk device, right? We'll log into the system, and then we check that virtio-blk device is in place, and try to run FIO traffic over that device, right? So here you can see that we are trying to log in. We've got our device. Yeah, it was too quick. So you can observe the FIO logs, right? And finally, we check that FIO was successful and we exit from the test. Suppose that's all for this presentation, for this demonstration. Yeah, and I'm giving the word back to Filip.
Thanks, Artsiom. Kate, can we see the slide deck again?
Yep, I am just bringing them up now.
Yeah, thank you. That's the right one. So first of all, thank you, Artsiom, so much for the nice presentations. So basically, you could see the interactive one, and then you could see that the integration tests can be run very easily, and they are also connected to a continuous integration system to be executed on every commit. And our summary would be that all that you have seen is already on GitHub. So here are even links to the recipes describing the exact steps that you can just go through on your own. And so the first link is basically to run the first demo that Artsiom was showing, and the second link is to the integration tests, and this one is even easier to run. Also, we indicated within the presentation that we are actively working on enabling multiple IPUs, real hardware platforms. So for any question on that, and in general for any detailed questions after this presentation and Q&A session, you can reach out to us. So either via Slack, there is a dedicated storage channel, or via email. We put here as the contact point then daily. And the last slide that we have prepared is the near future. So the improvements that are going to come with next IPDK releases. So this presentation was about a virtio-blk host-facing interface. And as a next step, we are working on enabling NVMe as an interface. I already said that we are working for support of hardware accelerated IPUs, both for acceleration of virtio-blk and NVMe. Also, an important functionality that many customers want is data at rest encryption. So IPDK is also going to support this soon. An important topic is quality of service. So our focus first will be on the enablement of bandwidth and rate limiters. Also important is, of course, the integration of the solution with popular orchestration frameworks, and Kubernetes is our main target. So there is work related to CSI plugin development. And further points are, for example, common management interface for virtual devices. So there have been already networking focused IPDK presentations, and we would like to have a common device management abstraction based on OpenConfig. One of other points that our work will be focused on is the virtualization use cases. So this was more like a bare metal use case, and connected to that live migration of VMs. And there are many more topics to come, as you suppose. And most of all, what I would like to say that this is a free open source project, so everybody is free to contribute, to propose and enable functionalities. And we are, of course, would like to hear from you. So what are the use cases that you would like to have enabled in APDK? And with that, I thank you for the time, for looking at the presentation, and we open up the Q&A session. We hope for some questions.
Yeah, I think this was really good, and we have this. This is recorded, so I know a lot of folks go and watch the recording later. But I think to get back to the earlier question of sort of what we're aiming to do here is both things that were described is try to provide this this abstraction layer so that on the host side or on the application side, they just see disks, and we can separate out the actual physical disks from the system itself, and we can control the type of disk that we expose, either virtio-blk or NVMe, and then we can use essentially software-defined storage to interconnect those virtual devices with some physical disks, arrayed out over the network. So this is getting us to a point where we can have a sort of a standard stack that we can put on different targets as we do these storage functions in a common way, using SPDK and trying to set up these common APIs through OPI and through IPDK. So this is the beginning of us starting to try to build this out and to be able to run it on lots of different platforms.
Yeah, hey, Guido Appenzeller here. Just want to say, fantastic progress. Great to see this going. I still think this is probably, one of the biggest impact technologies on the data center in the near future. So great to see this going ahead. One question: is there a new official party line answer on availability of hardware to actually do this beyond just containers?
There is not much update, but inside of OPI, what we're trying to do is get platforms that are available to developers. So maybe not to the public, but get platforms that a developer can get access to and test out applications. This seems to be the hardest thing, is that to build this ecosystem. If every single developer needs to have a copy of every different target to try out their application, it just doesn't scale. So within OPI, we're trying to figure out how we solve this problem. Certainly not, or we can follow up at least separately on the Intel platforms and their availability, but through OPI, we're trying to solve this problem generally, so that it just makes it easier to develop. Because right now it's you have all these different separated walled gardens that all need you'll all need a platform or a card sitting on your desk to test it out, and it's just it's sort of a mess. So we're really trying to solve that problem within OPI.
Yeah, makes total sense. Thanks.
And Guido, you probably know the SPDK model. So the tests are run also on different hardware platforms, and we definitely want to put a lot of attention and effort into having the quality and the testability of the solution as good as possible. So I suppose that pretty soon in the CI/CD infrastructure there will be hardware platforms connected and tests run of them. And if other vendors are going to enable support for their devices, they will also be supposed to get into this CI/CD execution on their platform, as this is already done in the case of SPDK.
Yeah, it makes total sense. I think getting a common software layer that's reasonably easy to adapt is probably one of the most important things here to drive this, to wider industry footprint. So I think it's exactly the right thing.
So I have a question. Okay, looks like there are other hands. So I mean, I'm trying to ask the other opposite of what was just said. It is great that we can have common API, but do you see custom stacks evolving, or because you could put a IPU on the storage side of things, and not just on the server where you're consuming it? And would you be able to support custom, because storage could be transformed into how the applications want to consume, not as a disk block, not as, not through the stacks that you have. There's a lot of value actually. First step, this is a great first step because we really need to be able to use it across multiple platforms. But the moment you do that, the programmability aspect of the IPUs, more than offloading infrastructure, suddenly becomes valuable. So maybe it's too far off, but any comments on that?
Yeah, I can comment on that. So you basically summarized it already. So it's a first step. So our focus is on this initiator-based solution, because we just need to face this work somehow. But of course the IPUs can be run in different modes. So there is also the target mode, where storage devices can be connected to the IPU, and it acts as a storage target. So this will be also a part of a future enablement. And in terms of customizing and adapting this solution, so there are two aspects to that. So first of all, it is an open source. So everybody can take the code and can take the solution and basically customize it as he or she likes. On the other hand, we are also trying to establish some standard interfaces. So this is why we have this OPI initiative together with Red Hat. And the standardization will be a big benefit from everybody. So the more people, the more actively people take part in the discussions and contribute their own use cases and requirements, the better APIs we can come up with.
Yeah, thank you. It's great. I know you said open source, free so many times. It still didn't sink in, I guess, right? So, but yeah, got it. Understood. Thank you.
There is a question from Dmitry.
Yeah, can you hear me?
Yeah.
Okay. Sorry, I had a problem with the mic. So I have a question around the storage APIs that will that will run at the APU side. I saw in one of your slides that you're planning to do CSI integration, but I think from the perspective of interoperability, it would make sense to have a separate service with, let's say, a standard API to consume storage at the IPU side, and then allow for different clouds to integrate it in various other purposes. Do you think it makes sense to have a service like that, or how do you think this would be approached in terms of interoperability across different cloud platforms?
Yes. So I'm not sure if I get your question right, but in terms of Kubernetes integration, so this is this solution. So this is work that is basically in front of us. So we are still doing some considerations. What's the best way of integration? There is an SPDK CSI plugin, and we are probably going to build on top of this project. And the first step is covering of the CSI node driver part of the solution. In terms of the integration with different storage appliances, there are so many vendors, and they have their own Kubernetes CSI plugins. In any case, these plugins are going to be used, and it is not our plan to replace these plugins. It's basically the solution is supposed to exemplify full system flow, and then the other vendors will need to kind of get it integrated with their own ecosystem. So does it help?
Yeah, a little bit. Maybe it would help if I gave an example. On the networking side, there's a project called OVN, which was kind of born out of the work that was done in OpenStack and in Neutron specifically. And now it's generic and it can be used by both OpenStack, Kubernetes, and other projects that might be interesting. And it now supports running portions of its services at the IPU or DPU side and fulfilling those requests. I was thinking about a similar thing, but for storage, if that makes sense. I don't know if you're familiar with OVN, so I don't know how this example will align with what you know.
Mm-hmm. Yeah, so I'm not familiar with this one, but you can definitely send me a link to this project, or reach out with the more detailed questions, so I can also take it later.
Okay.
I think that the first order bit is that what we're doing here is not the open source storage alternative to something like an OVN. We're not doing all of the logic that you would need to have a fully operational storage backend. Where OVN is kind of creating that virtual networking system across multiple devices. What we're doing here is mostly focused on the host interfacing to get that same device virtualization that you get on the networking side. We're doing it here with virtio-blk and NVMe. But the logic to map those virtual devices into multiple copies somewhere in the system, or do erasure coding, or have all the redundancy you need, and get the right performance, and worry about all the different blast radiuses and things like that. That is not here, and it kind of is related to the previous question of sort of, hey, how do we get to that open source solution for that storage backend, which doesn't really exist. So this is really something that will live underneath that type of solution. So right now, if you had a nicely designed NVMe over Fabric or NVMe over TCP backend, you could sort of plug that in on top of this work that's been done. So I think that there needs to be the OVN equivalent for storage that can do those types of things. OVN has quite a few features to be able to handle that at scale, and that just doesn't exist today in storage. And yeah, it's definitely screaming out for an open source project or someone to contribute what they have in the open source, so that we could hook that up to what we have here.
Yeah, okay, that makes sense. So that kind of confirms my thoughts about this being a building block for like a larger control plane project. Thank you.
So this SMA is the kind of API that is supposed to be vendor agnostic, and it's supposed to be extendable in a way that it can integrate with different frameworks. So I mentioned Kubernetes here as a first step, but OpenStack is also an important integration from our point of view, and it will get especially important as soon as we as we get more into the virtualization use cases.
Yeah. Okay. Thank you. I think I got what I need. Thanks a lot for taking the time to answer the question.
By the way, if you have some question of this type, so my proposal would be to go with this question to IPDK Slack and post them there, so that we can initiate the discussion.
Okay, sounds good. I'll join that channel.
Excellent. Are there any other questions?
I think we're good. That was great. Thank you, guys.
Thank you, everybody. Thank you, Artsiom, for the great demo, and thank you all for the participation.
Thank you, everyone.
Yeah, thank you. Great work.
Thank you. Have a great
Thank
day.
you.
Thank you.
Have a good one.